All right, so what we're doing today is we're continuing with related rates. That's what we lopped off of the last unit to squeeze that in before the end of the quarter. So we're continuing, or we're starting related rates. We'll be doing related rates today and Wednesday. Today we'll focus on ones that don't require trig, and Wednesday will require trig, so don't forget that. So with numbers 1 and 2, what did we have to use when we did numbers 1 and 2? It's 2 words. Noah just whispered it. And I hear some more whispering it. Implicit differentiation. Remember that? So related rates requires us to do implicit differentiation a ton. So you cannot forget about, that's our warm-up equipment. So it asks for us to find the h dt. So that's our derivative of h with respect to t. Which means anytime I take the derivative of anything other than t, I need to write d whatever it leads to. Let me reorient this for the third time today. See if it looks a little better. I apologize in advance that Smartboard has been rebelling today. Okay, so here we should get 4h dh dt. So again, we are doing everything with respect to t, so if our variable is not t, we have to write that implicit after. Alright, then here we have minus 6t squared. That was t, so we don't have to worry about writing the implicit after. Derivative of 32 is nothing, and derivative of t is just 1. Are we good with this? Okay. So then our dh dt, when we solve for it, would be 1 plus 6t squared. Good with that? Yes.
Would it be the same to solve for h?
Yep. It's just not always easy to solve implicit or to solve explicitly for h. Alright, so then for number 2 here, did I lose my h? Oh, thank you. Now are we satisfied? Does anyone know what 4-H is? Like the club? Yeah, like 4-H camp, where you like take projects and you learn skills, and if you have animals, you show your animals. Yep. It exists in Fairfax County, I promise you, because there is a fair for it.
Oh.
There you go! Well, no, so the camp you don't bring your animals. It's if you do 4-H, you show your animals at the fair. So they like legitimately have farm animals out there? That's awesome. Thank you. So where I come from, 4-H is a very big thing, and I did not ever take animals, but like you can raise pigs and show your pigs and sell pigs. And the fair, the county fair where you show all of your stuff, happens at the end of August, and when they changed the start of the school year, so we used to start after Labor Day, now they start before Labor Day, but they take off the week for the fair. So they literally go to school, like starting August 15th, go to school for about a week and a half, and then take off a week for the fair, and then they go back to school again. Because everyone's at the fair showing their animals.
Is there a one?
No, it's just like you work all year long, and then you get judged on your projects, you get judged on your animals and whatnot. And then in August is when they show. It's a little bit of a different role. So that's 4-H. That has nothing to do with what we're doing here. That was a side note. Okay, so for number 2, it says find the derivative with respect to t. What is different between number 2 and number 1? There is no t. Good. If we notice 2, it's not specifying the derivative of a particular variable. So we're just taking the derivative of the whole thing with respect to t. So, again, with respect to t, anytime I take the derivative of a variable other than t, I must do implicit with it. So I have 4h dh dt plus 9y squared dy dt plus 4 dk dt. So again, this notation just simply means the derivative with respect to t. This is going to be similar to what we're doing with our related rates. Essentially what we have is that we have more than one rate happening in a scenario, so we have to write an equation that relates the variables, and when we take the derivative, we have to do it implicitly, and we have multiple rates that show up within that derivative, and then we substitute information down from there. But a reminder of implicit differentiation before we dive into this. Questions with that?
So you just leave it like that?
For this particular problem, yeah, because it's just saying find the derivative of this expression with respect to t, so we'd leave it at that. Whereas before it told us specifically which variable to solve for. Okay. So what you'll see on your notes with Tweety Bird there within it is our day 1 for related rates. Okay, so again, in a related rates problem, you have an equation relating 2 or more things that change over time. So thus we have 2 or more rates that are happening. And we want to find the rate of change of one of those things. So, for example, with this first one, we have Tweety's resting in the birdhouse, and there's a ladder leaning up against the birdhouse. So we have that the ladder is being pulled away, so thus it's falling down. So the height of the birdhouse, or the height that the ladder is leaning up against it, is changing, as well as the distance from the birdhouse to the ladder is also changing. So we have multiple things that are changing at the same time. So we have multiple things happening, different rates happening, but they are related within that problem. So go ahead and just take a moment, read through your steps here. I trust you can read, so I won't read it to you. You're going to take a moment to look through that. So, again, it's often helpful to draw a diagram to have an idea of what's happening, just like in our optimization problems. Sometimes the diagram is given to you, sometimes not. And then make sure you identify all pertinent information that's been given to you. Sometimes they will give you more than you need, so just be aware of that. With your picture, always write in what variables you're using. Because, especially on pre-response problems, you might choose a different variable than someone else. And so if you don't specify what your variable is representing, then the grader's not going to know for sure exactly what you're referring to. Alright, so we're going to write an equation that gives the relationship between the variables. So, for example, with Tweety Bird and the birdhouse, we have 2 sides of a triangle that are changing. So probably Pythagorean theorem would be a helpful formula for us to use. So we're going to want to come up with an equation that relates to the variables that we're dealing with. And notice it says, do not substitute given information until after you have taken the derivative. I want you to put a note next to this. So any number that is a fixed number, so fixed numbers can be substituted in from the start. Alright, but if we have any values that are changing, we don't want to substitute those until after we've taken the derivative. Alright, and then our big thing that we'll be doing is implicitly differentiating. Then we fill in our information and solve for the unknown rate that we're looking for. And in the end, make sure you actually answer the question, just like with optimization. So it's going to be similar to optimization that we're dealing with multiple pieces and various equations, kind of relating what we're working with. But with related rates, we have multiple rates that are happening, whereas optimization, we're trying to maximize the value. Okay, so let's just go and dive in with example 1. Keep forgetting. Alright, so Tweety is resting in a birdhouse 24 feet off the ground, using a 26-foot ladder, which he leaned against the pole holding the birdhouse. Sylvester tries to steal the small yellow bird. Tweety's bodyguard, Hector the dog, apparently that's his name, starts pulling the base of the ladder away from the pole at a rate of 2 feet per second. How fast is the ladder falling when it is 10 feet off the ground? A lot happening there. So let's go and draw a picture. So I've got Tweety Bird's house on top of a pool. And we've got a ladder coming down. Your pictures do not need to be elaborate. This is already more detailed than is actually necessary. In the ground. All right, we know that Tweety Bird's house is 24 feet off the ground, and we know the ladder is 26 feet. Does the ladder's length ever change? No. So we can go ahead and keep it. That is a fixed value. The ladder's length is not going to change. Now what's happening, Hector starts pulling the base of the ladder away from the pole. So I have my ladders being pulled away, and it's at a rate of 2 feet per second. And then they ask how fast is the ladder falling when it is 10 feet off the ground. So I know that this height is also going to be going down. And that's what we're trying to find. We're trying to find this right here. And now they're asking specifically how fast is it falling when it is 10 feet off the ground. So we're taking a snapshot in time. The moment that it's 10 feet off the ground, what is the rate at which it's falling? Okay, so let's go ahead and assign some variables. You can use X, Y, Z, A, B, C, whatever you feel like. What did I use? I think I used A, B, and C. So I'm going to go ahead and call my side over here A. And this down here I'm going to call B. And then this is C, but again, that's a constant. So it's not really necessary to call this one a variable. That's good. All right, so we can see with their picture, probably Pythagorean theorem is going to help us relate all of the variables in there. We can see that both A and B are changing. So there's two different rates happening. The rate at which the ladder is being pulled away and the rate at which the ladder is falling. The rate at which that distance is decreasing due to the ladder falling. So it's good for us to identify what we know and then take a look at what they're asking for and try to piece it together.
The height of the birdhouse.
The height of the birdhouse actually does not matter. So if we think about it, we can say, okay, this birdhouse is 24 feet off the ground, right? But does that impact my height of the ladder at all? No. So I mean, I know that it's going to start off at 24 feet off the ground, but we don't really care because we only are interested in when it's 10 feet off the ground. So this would be a case in which this piece was not actually necessary for us to do this problem. Are they always going to throw in extra information? No. In fact, I feel like it's more often that they don't give you extra information, but sometimes they do, so just be aware of that. Okay, other questions before we go and start? So I like to go ahead and identify everything that I know, from what's been given to me to what I know about the situation. All right, so we know that C is 26 feet. That's not changing, right? That's a fixed value. We know that the rate at which my distance B is changing is 2 feet per second. What is the calculus word for rate? Derivative. So what we're saying here then is that dB dt, the rate at which B, the distance, is changing with respect to time, is 2 feet per second. Also, if you think about it, distance over time, feet per second. So that also gives you an indication of the rate. They did not tell us anything about the rate of A. That's what we're trying to find. And we do know that we can use the equation A squared plus B squared equals C squared. That helps relate all the information. And then I don't think there's anything else really that's been given to us. So let's go take a look at what we want. What are they asking for? Yeah, we want to know how fast is the ladder falling. What would that be in terms of our picture? Yeah, dAdt. I want to know the rate at which A is changing. So I want to know dAdt specifically when it is 10 feet off the ground. So what would that value be? Yeah, specifically when A is 10. Okay, so we're taking a snapshot in time. We're pausing at the moment that A is 10, and we're going to figure out what our rate is. Questions on where any of this came from? Okay. So let's go ahead and take our equation here. Now again, since this is a fixed value, I can go ahead and substitute that in before I do any derivative. So I have a squared plus b squared equals 26 squared. Notice I'm not putting 10 in for a because a is changing. So we don't put in any changing values until after we've done the derivative. Okay, let's go ahead and do our derivative. And remember, we're doing this with respect to time. So it's implicit differentiation here. So we would get 2a dA dt plus 2b dB dt equals, what's the derivative of 26 squared?
0.
Nothing. 0. Okay. Now, we are looking for, we are looking for this value here. Let's make sure we do have all the rest of the information. So I'm looking specifically when a is 10. So I'm going to go ahead and write that in. I think that's going to do. So when a is 10, and I have 2 times 10. I don't know dA dt, that's what I'm solving for. Plus 2, what's my b value? Yeah, we can take, we don't know it right now, right? But we know that when a is 10, we have that Pythagorean theorem, 10 squared plus b squared equals 26 squared. Right? So at that moment when a is 10, I'm finding what is my b value at that moment. Does that make sense what's going on there? Questions with that? Okay. Go ahead and figure out what b is. If you have your calculator, you may use that. Thank you. What did we get for our b value? Should be a nice number. 24. Now, again, we know it's plus or minus, but we know in the context of our problem, we cannot have a negative distance. So when a is 10, b is 24, I personally like to go ahead and write that information in. It's not necessary because we've already given that specific moment in time by saying when a is 10. I just like to rewrite it for my own personal use. All right, so 2 times, again, when a is 10, we know that in this situation, b must be 24. And what is my dB dt? Good, it's the same grade of 2 the whole time. Now, I want to point out something before we solve for dA dt. Our rate here, 2 feet per second, is positive. It will not always tell you whether it's going to be positive or negative. You have to stop and think in the context of the problem. What do we have? Whenever my distance is growing, my rate has to be positive, right? Because I have that increasing distance. And when the first derivative represents increase, it means when the first derivative is positive, it represents increase. When I have that rate is negative, that indicates that the distance is decreasing. So again, if my distance is getting smaller, then I should have a negative rate. Here it says Hector is pulling the base of the ladder away from the pole at a rate of 2 feet per second. So it's going away from the pole, which means the distance is increasing. So it's that positive rate. So before we solve, would I expect dA dt to be positive or negative? Negative, because that distance for a is decreasing. All right, so let's go ahead and solve for dA dt. And we'll leave it as a fraction. What do we get for our final rate? negative 24 over 5. Make sure you always give units. If units are given to you, what would my units be for this? Feet per second. Good. The distance is feet, and the time is seconds. Now, here comes the kind of trick. Make sure you answer the question. So it says, how fast is the ladder falling when it is 10 feet off the ground? Falling already indicates that it will be a negative amount. So the ADT is a negative rate, but the rate at which it is falling would be, it is falling 24 feet per 24 feet per 5 seconds, or 24 over 5 feet per second. We don't want to say the ladder is falling at a negative 24 over 5 feet per second, because you're basically doing you're negating a negative, you have a negative. So the fact that it says how fast is the ladder falling already indicates that it will be a negative rate. So we want to go ahead and when we answer the question, say the ladder is falling at a rate of negative 24. Oh, I just said what not to do. Do as I say, not as I do. As a rate of 24 over 5%. Now, if they just said how or what's the rate of the change in distance, so if they didn't specify really direction with it, then you would go ahead and say the distance is changing at a rate of negative 24 over 5. And in fact, you could even say here, the ladder's height is changing at a rate of negative 24 over 5. But if you have that wording in there to indicate already that's going to be negative, you don't want to keep the negative with it. I feel like most times AP will not use already the wording to indicate negative, but be aware they might. So just keep it. Okay. So this is our final answer. Questions with that?
Would you want to indicate that it's when the ladder is 10 feet off the ground?
That is a good question. That is good to do. Now, since they specify that in the question, you're good to not restate it. But you're correct. The ladder's falling at this rate specifically when the ladder is 10 feet off the ground. But again, since they specify it there, you should be fine. But I like that. I'm going to write it in. Now, related rates questions often show up in free response. Are you going to see it more than once in a free response? Probably not. On one particular test, you would have it probably no more than one time in a free response. But they also show up in multiple choice. So keep in mind, in multiple choice, you don't have to be all super nice and neat and detailed with your information. Free response, you definitely want to be detailed with your information. They're looking for you to have this beginning equation here. They're looking for you to label your information on the diagram. They're looking for that derivative. They're looking for when it's plugged in. So make sure you are detailed and organized with your work for free response, multiple choice. You just do whatever you need to do to get this answer. All right. Questions with that before? It's really not too bad. It's a lot at first. But after we do a few of them, we're like, oh, it's really not too bad. It's similar to optimization, again, that we're taking the derivative. Again, this is applications of derivatives, but there's definitely more pieces here. All right, go ahead and read example 2. We're solving life's questions here. Alright, so we have a Tootsie Roll Pop, and it is a sphere. And we're not actually calculating how many legs it takes to get the center of the Tootsie Pop. I think Stats actually does that, where they do like trial runs with it. I'm not sure. Take Stat and find out, I'm sure. But they tell us that it is giving up volume at a steady rate of 0.25 inches cubed per minute. And then they ask, how fast will the radius be decreasing? We're looking for, specifically when the Tootsie Roll Pop is 0.75 inches across. And very kindly, the formula was given to you here. Indeed, there's some sneaky stuff in here. Alright, first let's go and draw a picture. Sometimes you don't really need a picture to get an idea of what's going on, but I think it's cool. So I've got this Tootsie Pop. And they tell us that it is giving up volume at a steady rate of 0.25 inches cubed per minute. What is this representing? The rate at which it's losing volume. How do we know that it's volume? Oh, well, I guess it says volume. So if it doesn't say the word volume, how else could I have known just from this implication that it's volume? Yeah, the units, it's inches cubed. Good. So let's go and just add this to our no column. So we know that dV dt is 0.25 inches cubed per minute. Is that going to be a positive or negative? Negative, good. I like to go ahead and mark that in the information. Why is this negative? Yeah, it's giving up volume. It's getting smaller, so the volume is decreasing. Good. And they told us really not much more information than that. Okay, so we've got our volume equation, 4/3 pi r cubed. I will tell you this is an equation that you definitely want to have memorized for the AP exam.
What's the list of like equations?
You get no, like in physics, you get like a piece of paper with a whole bunch of stuff. You don't get that for calculus, but sometimes they will give you an equation within the problem. But it's not guaranteed. I've seen them give sphere, and I've seen them not give sphere. So this is one that they would expect you to. That's a good question. Okay, and what are they asking for? What do we want to know? What rate are we looking for? Yeah, when the radius is decreasing, so we want dr dt. Specifically when the Tootsie Roll Pop is 0.75 inches across. What is the 0.75 representing? The diameter. Sneaky sneaks. So it's when our diameter is 0.75. So what would be our radius for that then? 0.375. Okay. So I'm going to go and draw my radius here. And conveniently, our equation only has one variable within it. My volume is based on just radius. So that's actually pretty nice for us. A little bit less work. Okay. There's not really any other information given to us. Let's go and dive in with it. Alright, so I'm going to take all this information. So my volume is 4/3 pi r cubed. Do I have any fixed values for this problem? No, my radius is changing, the volume is changing. If you think about when you're looking at Tootsie Roll Pop, the radius is constantly changing, the volume is changing. Has anyone actually tried to make it to the center without chomping on it? No. Has anyone been successful? I can't. It just takes forever. Just keep looking. You got it. Alright, so let's go and take our derivative with respect to time. And so our 3 comes down and cancels. That's nice. R squared dr dt. Okay. And let's fill in what information we have. What is my change in volume? What's the rate of it? Good. Negative 0.25. 4 pi. And we are looking, oops, I should have squeezed that in. When r equals 0.375. Okay. So when my radius is 0.375, so now I can go ahead and put in 0.375 and dr dt, which is what we're solving. So again, this here that we found is going to allow me, notice it's relating the rate of volume with the rate of the radius, how they change. We are saying, all right, pause at the moment when radius is 0.375. That is what we're interested in. So I could use this for any point in time. I could say, hey, well, what is that rate when the radius is 0.25 or when the radius is 0.1? So this models that change or the relation between those two rates, and we are pausing our time and saying, at the moment when radius is 0.375, then I'm going to find my rate. All right, so let's go ahead and solve for dr dt. Solve for dr dt, and I want it in fraction form, don't multiply your your pi. What did I lose? I do, thank you. What did I do without you guys? I promise I did it on here. It's right there. Alright, so go ahead and solve for DRDT in terms of pi. And I don't want decimals. So again, leave it in terms of pi, and I want the fraction, not decimal. For those of you that are doing it without a calculator, just to exercise your brain muscles, that radius is 3 feet. Once you think you have your DRDT, you can compare it with something else. And should we expect our DRDT to be positive or negative? Negative, good, because my radius is shrinking. Alright, what do we get for DRDT? Good, -4/9 pi. And my units for this? Inches squared, or inches cubed? Inches. It's just a radius. Radius is measured in single units. So inches per minute. Alright, now again, let's make sure we answer the question. Notice once again they used wording that indicates that our rate would already be negative. It says how fast would the radius be decreasing. So we want to make sure we answer accordingly. The radius will be decreasing, and the fact that we said the word decreasing indicates we don't need to give that negative. Decreasing at a rate of 4/9 pi inches per minute. Definitely make sure you give units. It's very common for a related rates problem that they give you units, and that point values will be assigned specifically to whether or not you gave units. So even if your answers were wrong, you can still get at least a 1 out of 9 for units. Yes.
The pi belongs to the bottom, right?
It does. The pi belongs to the bottom. And for those of you that perhaps write your fractions like this, make sure, I would recommend you write it as a vertical fraction to just clearly show that pi is in the bottom. Otherwise, sometimes some of your guys' fractions look like this, which would be 4 pi to the 9. So make sure your pi is clearly in the middle. Also, remember, if this was truly free response, did we have to simplify all that mumbo jumbo? No, we could have just said, well, not a complex fraction, but we could have multiplied by the reciprocal of what we got. Okay, questions on that? Okay, so let's take a look at our next one, which brings geometry back once again. So when you were in geometry many moons ago, around December-ish time, you learned about similar triangles. Similar triangles comes back once again with interrelated rates, and it's a decently common type of problem that you'll encounter. And in fact, really it comes back not just with similar triangles, but also with similar shapes. Like with example 4, we'll see that there's similar ones. All right, this one's kind of weird. So light on the ground, 100 feet from a building, is shining at a 6-foot tall man who is walking away from the streetlight and toward the building at a rate of 4 feet per second. How fast is his shadow on the building becoming shorter when he is 40 feet from the building? All right. So we've got a nice picture here. We've got our light on the ground, our dude that's 6 feet tall. Doesn't matter how tall the building is, but they're wanting to know. Well, let's go and fill in what we have. Okay, so our building is 100 feet away. 6-foot tall guy. All right, so the guy is walking toward the building at a rate of 4 feet per second. All right, so I went ahead and called the distance between the light and the gentleman here, x, and he is moving at a rate of 4 feet per second. Notice he's walking away from the light, which means his distance is increasing, so it is that positive rate. And they want to know how fast is the shadow on the building becoming shorter when he is 40 feet from the building. So his shadow on the building, so I went ahead and called that y. And it says how fast is his shadow becoming shorter. So I know that my shadow is going to be decreasing, so thus we should expect that rate to be. Alright, so what we have here are similar triangles. Let's revisit the world of geometry for just a little bit. Now, in these types of problems, we like to believe that the gentleman is standing upright, thus he is perpendicular to the ground, and that the building was also built upright, and thus is perpendicular to the ground. Of course, if this was the Leaning Tower of Pisa, we would have to adjust that. But whenever we encounter problems like this, we are safe to assume that they are both upright and thus perpendicular to the ground. Now, in the world of geometry, if two lines are perpendicular to the same line, we know these two lines are parallel. And if these two lines are parallel, we know that we have corresponding angles congruent. Likewise, the small triangle and the big triangle share this top angle, which is reflected properly. So in this scenario, we have that comparing the small triangle to the big triangle, we can prove the triangles are similar by the angle similarity postulate. Now, everything I just told you is not necessary for you to do on calculus. All I'm telling you is that that is the reason why I can say the small triangle is similar to the big triangle, okay? So in this case, when we have small and big are similar, then I can say, I'm going to go and just fill in some values here. I can set up a ratio or a proportion of small triangle to big triangle. So I'm going to go and outline my small triangle here. So small triangle to big triangle equals small triangle to big triangle. This, when I have similar triangles or similar shapes, it allows me to set up that proportion. So I can say for this particular example, A to B, the vertical of the small triangle compared to the vertical of the big, is equal to small to big. Now notice big would be D plus. Okay, so what I'm doing is small to big, small to big. So that's the generic case of what's happening. So for our picture here, we could set up the ratio 6 to y equals x to 100. You see it there? So again, that height of the man is not changing, so that's why I can go and fill in that fixed value. The distance of the building and the light is not changing, so that's why I can fill that fixed value. But again, I went small to big, 6 to y, x to 100. So knowing that they're similar triangles is what lets me set up this equation here. Questions with that? So you don't ever have to prove by angle similarity postulate the triangles are similar. You did your time with that in geometry. We just simply need to know, hey, similar triangles, I can set up that proportion. Okay, so let's go ahead and talk about what we know. So let's see, I have that dx dt is a positive 4 feet. Again, his distance is moving. Positive 4 feet per second. Again, we have that constant 100 and constant 6, but let's just go and put that into our equation. So we know we can use the equation 6 over y equals x over 100. And And then let's take a look at what we want. Alright, they want how fast is his shadow in the building becoming shorter when he is 40 feet away. So we want dy dt. We let that represent the shadow. Specifically when he is 40 feet from the building. What variable is that representing? Ooh, they changed it up on us, didn't they? They're saying when this is 40. So how much would x be? 100 minus that, 60. Be careful. Okay, so we want when x is 60. Okay, questions on all of our information there? Feel like revisiting geometry? Spark, tell Ben it comes back. Alright. So let's go ahead and take our equation here. Again, this is the equation that relates our two variables. So we have, here because we're taking on this, 6 over y equals x over 100. We're going to take our derivative. I probably would rather write this as y to the negative first, so I'm going to write that a little different. I just like to take the derivative with me. Yes. Yeah, you could also do cross product for sure. There is one of these problems where it's advantageous for us to do cross product, but here it would result in product rule, which is fine. You're more than welcome to do product rule. But yeah, you can do cross product and then take your curve that way. Alright, so let's go ahead and do our derivative. So on the left side we get negative 6 y to the negative second dy dt. What's my derivative on the right side? 1 over 100 dx dt. I don't like that arrow, it's throwing me off.
I completed all your first one.
Right here. So bring down the negative 1, multiply so we have negative 6. Reduce your power by 1, negative 1 minus 1 is only negative 2. So power will bring down your power, reduce your power by 1. Oh, the beginning thing there? 6 over y is the same thing as 6 times y to the negative first. So I brought it up just to make it easier. Other questions so far?
Yes, I want only to
Why did I put it? So before when we did implicit differentiation, we were looking for dy dx, right? So x was the variable I was taking the derivative with respect to. But now I'm doing it with respect to t. So anything that's not t, I have to do that implicit afterward. Yeah. Yeah, be careful, guys. And it might be to your benefit to not use x and y if you get confused with that. But our previous implicit differentiation, we were taking the derivative of y with respect to x. Notice we're taking it with respect to t. So anytime it's a variable other than t, you have to do that implicitly. It's a good question. Other questions? Okay, so let's fill in what we do know. Do we have our y value? No. We only had when x was 60. Alright, so we know we're looking at when x is 60. But when x is 60, what is y going to be? How can we figure that out? Yeah, we've got the formula over here. So let's just go and do that off to the side. Let me erase all my mumbo jumbo there. So when x is 60, let's see, we have 6 over y equals 60 over x. Whoops, 60 over 100. And what do we get when we solve that? 10, good. Okay, so when x is 60, y is 10. And now we can take that and plug it in. Alright, I'm going to put that back in fraction form. So I have negative 6 over y squared, so it's 10 squared, times dy dt. We don't know that, that's what we're looking for. Equal to 1 over 100. And what was our dx dt? 4. Alright, go and solve for dy dt. Now, A lot of times your related rates problem would be on a calculator portion, but there are sometimes that it is not calculator. This would be one that would be fair to be non-calculator, but let's use the calculator to make it a little bit easier. Alright, what do we get for our rate? Negative 2/3? Negative 2. And again, we want to use our proper units. Now, again, let's take a look at what they asked. How fast is his shadow on the building decreasing? They used that word already, so we want to answer it without that negative. The shadow is decreasing. At a rate of 2/3 feet per second. So what we should expect is at that exact moment in time, the moment he is 40 feet away from the building, his shadow is decreasing basically 2 feet for every 3 seconds. Okay? Questions with that one? Still feeling okay? That's really the craziest that it gets. Alright, so let's take a look at our cones. Water runs into a conical tank at a rate of 9 feet cubed per minute. The tank stands vertex down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet? So I have this big tank here, that's the outside one. And then what they have drawn inside here is our water level. I'm just going to go ahead and fill this in so I know that that's the water versus the tank. It's going to be a great ice cream cone problem. Alright, so it says water runs into the tank at a rate of 9 feet cubed per minute. And they tell us the tank has a height of 10 feet and a base radius of 5 feet. So here we have that cone within the cone. Again, we have similar shapes. And if you look at it, I have this guy here compared to this guy here. So once again, we have those similar triangles. So we know that we can set up our ratio. Now we do have a couple of constants or fixed rates here. Notice my radius of the tank and the height of the tank does not change. It's the radius and height of the water level that's changed. Okay, so let's fill out what we do know. Alright, let's go set up that equation. So 5 over r equals 10 over h. Or you could have done 5 to 10 r to h. That way probably would have been a little bit nicer. And they told us water runs into the tank at a rate of 9 feet cubed per minute. So what is that 9 feet cubed per minute representing? The change in volume. So that can be positive or negative. Positive. And we're wanting to know, let's see, how fast is the water level rising when the water is 6 feet deep? So what rate would that be? We've got both R to choose from and H to choose from. Yeah, it'd be our H. Water level rising is talking about that height. So we want to know dH dt, specifically when the water is 6 feet deep. What is that 6 feet representing? Again, H bit. So specifically when H is 6. All right. So we have this equation here, as well as we have our volume equation. Now, when I go to do my derivative of my volume equation here, as it stands, I would have to do product rule with R and H, and in doing product rule, I'd have dr dt, dH dt. Do I know dr dt? Was that given to me? Do we see dr dt? No dr dt anywhere. And that causes issues for us, because it would be a lot of work for us to find dr dt to be able to plug it in. So before we even take our derivative, what could we do so that we only have h with it? Take a look what's been given to us. What could I do so that I have only h within my equation? Yeah, we can use this equation here and solve and substitute it in. I only want to have h because I only want dh dt. I have no information about dr dt, so I'd rather not deal with it if I don't have to. So let's go and solve for r so that I'm substituting in h. Okay. So let's go and solve for r here. I mean, I guess I'll go through and cross multiply for you guys. Are the cookies still? Sounds like the oven timer's. That's what my oven timer sounds like. Alright, so what does r equal? 1/2 h, or h equals 2. So now I can take that and put it into my volume equation, and now it'll all be in terms of h, and it'll make our lives a whole lot easier. You can certainly do product rule and do some more work to get there, but I promise you it's going to be more. Alright, so let's go and take our volume equation. 1/3 pi r squared, which we know is h over 2 squared h. Let's simplify that a little bit. We can simplify that even more. Let's say we get 4 in the bottom, so pi over 12 h. Are we okay with that equation? A lot nicer now to work with. Alright, so now let's go ahead and do our derivative. Everything with respect to time. Why am I only writing dv dt here? Why is there not still a v? Because when I do my derivative of h, I'm going to have h squared dh dt. Why am I only having dv dt? Yeah, because the derivative of v would be 1 dv dt. Good. I just didn't want you guys to think I was neglecting v altogether. Alright. So bring down my 3 and simplify, get pi over 4 h squared dh dt. So again, there's my generic equation relating the change in volume with the change in height. And we are looking specifically when h is 6. Alright. We know our change in volume is a positive 9. Pi over 4 when h is 6. So 6 squared. And dh dt is what we're solving. Okay. Go ahead and solve for dh dt, see what you get. Are you keeping the pi? Yes, I want your answers in terms of pi, thank you. And guys, if on a test it's not in terms of pi, please do not punch in 3.14. Please actually use the pi button. That will greatly affect your answer if you do 3.14. Alright, what do we get for dh dt? 1 over pi. Kind of an interesting one, isn't it? Alright. We want to use our units and make sure we actually answer the question. How fast is the water level rising when the water is 6 feet deep? So we should expect it to be positive. We see we did get positive. And let's make sure we use proper units. So it's height. So it's feet per minute. Okay, now we're ready. We're green. For this problem, since we don't have to worry about the wording of it, it's fine to just go ahead and box this. But it's still, of course, nice to say the water level is rising at a rate of 1 over pi feet per minute. But again, since we don't have to worry about the wording of it, you can just box it. Questions with that? Okay, I feel like I need to let you guys try one on your own now. Let's take a look at example 5. Oh, look, it works now. An oil tanker spills oil that spreads in a circular pattern whose radius increases at the rate of 50 feet per minute. How fast are both the circumference and the area of the spill increasing when the radius is 20 feet? So I want you to go ahead and try part A here, and notice they're asking for both the rate of change of circumference and the rate of change of area. So you're actually looking for 2 different things. So go ahead and try A. Think of what your area formula is and your circumference area, or your circumference formula. Feel free to talk with those around you if you get stuck and ask me questions, but I want you guys to go ahead and try this one. Let's have you take... There's your back. Alright, while you guys are doing that, I'm going to go ahead and fill in information up here. But keep working, and then you can kind of look back and see as we go.
I got nothing. I don't know.
I just like the notes.
I'm like looking at the other problem.
I like what I don't know. No.
I think I'm going to start off with the circumference.
Wait, what was your question? My bad. Yeah.
So we know one of them because it's there. Is
Circumference.
so DA is actually I got a little number like
Oh, very nice.
And then and then we just substitute.
So guys, if you notice with your circumference and area formulas, notice there's only one variable we have to worry about, which means our lives are automatically easier. Because before we would have to substitute in using the similar triangles and whatnot. Not so much here.
What?
Yeah. What?
No, I got 105. I got 105.
And 300.
I got 2,000. Maybe I added my extra zero somewhere.
Oh, is that this?
Let's see. I think I did. No, I didn't.
What? How? How did you get 2,005?
What'd you get? 205?
Yeah.
I got 2,000.
How'd you get 2,000?
20 times
Times 2 is not times another 20, baby. Hey, don't need a calculator. Don't need a calculator. What?
And I did it both ways too.
Oh, yeah, I'm being dumb. Sorry, you're right. You're correct. You were correct.
Oh, this is a big circle. That makes sense because it's an oil tanker. Yeah. Did we get our dCdt was 100 pi?
Yes.
Now, before I move on to area, what do we notice about our dCdt equation? What is it lacking? Did it matter that my radius was 20? No, there's no r within here. So regardless of how big my radius is, the circumference is changing at the same rate the whole time. Interesting. So can I know dCdt for b here?
Yes.
Yeah, because it doesn't matter what my radius is. So if I were to go through the same process, again, I would have no radius to substitute in, so I automatically know that's going to be 100 pi. Alright, but we do have to do some more work for area. But before I move on to my area, do you have questions as to what I did so far? Are you with me? You good? Made me nervous with that device in here. Alright, so now let's take a look at our area. So dAdt equals 2 pi r dr dt. Notice now my rate of change of area is dependent upon that radius. So we do have to do when r is 20. So we get 2 pi times 20. And my dRdt was 50. Ooh, what's the answer for that? 2,000. Get it, not 200. 2,000 pi feet squared. Good. Perfect. Why was dCdt just feet then? Yeah, it's just the circumference, which is just a single unit. Questions on that one? Okay, so then to get that thing done here for B, dAdt would be specifically when we're at 50 feet. So we have 2 pi, and it was times radius, which is 50, times dRdt, which is 50. Right, what is that number going to be? I like to do the 2 times 50 is 100, and then times 50. Alright, and again, that's feet squared. Does it make sense for my area to be a positive rate? Yeah, oil's spilling into it. The radius is increasing, so hopefully my area is also. Okay. Alright, questions with that one? Alright, let's see. Let's go take a look at 6. It's still similar, but I want to make sure we get our derivative okay. Yeah. Alright, so number 6, the particle is moving along the curve whose equation is that. The x-coordinate is increasing at the rate of 6 units per second. When the particle is at that point, at what rate is the y-coordinate of the point changing at this distance? Alright, so I want to just make sure we at least have a setup right for this. We don't really have to draw a picture for this. In fact, I don't know what this looks like. I don't know if you know what it looks like, but I'm not really sure what that looks like. So that's okay. We know that we're dealing with x's and y's. So we have the x-coordinate is increasing at a rate of 6 units per second. So dx dt is positive 6. And what else did they say? We have our equation, and we want to know the rate at which the y-coordinate is changing. We want dy dt, specifically when the particle is at the point 1, 2. What does that translate for us? Good. When x equals 1, y equals 2. Oh, how nice. They already did the math for us. They could have said when x is 1, and then we would have had to do all the math to find our y value. How come? Okay, questions?
Wait, does that point not go with the rate of 6? Since it says the x-coordinate is increasing when the particle is at the point 1, 2?
Good point. So, yes, thank you. This is when x is 1 last. Thank you, Reed. Because our x value is not changing at the same rate. Good. Alright, other questions? So what equation am I going to use to manipulate? What am I going to take the derivative of? The one they gave us. Doesn't that look like a nightmare to take the derivative of? We've got product rule within quotient rule, but let's use what Mr. Noah said earlier. What if we cross multiply that guy? then it would go a lot nicer for us. We'd have 5xy cubed equals 8 times 1, so 8 plus 8y squared. Isn't that a lot nicer? Take the derivative of? Yeah, we still have the product rule, but at least it's not product with the quotient. So this would be what we're going to then do the derivative of, and then again specifically when x is 1, y equals 2, we can fill in stuff. Okay, I just want to make sure we have this set up for that. Let's now take a look at example 10. I want to make sure our setup for that is okay as well. A rowboat. Not this but a dream. Okay. Example 10 here. I changed yours so that it works out a little bit nicer, and I think yours says 6 feet above. Still 2 feet per second, and when the amount of rope spill out is 10 feet. Is that what you guys have? Yeah. Okay. Numbers are a little bit nicer this way. So let's draw a picture for this, because it's kind of a weird one. So we've got a dock, some planks of wood, and we have a rowboat being pulled toward the dock. So I'm going to draw my rowboat here. I know it's not a sailboat, but for me to know that it's a boat, I need a sail on it. And it says the rowboat is being pulled toward a dock from the bow through a ring on the dock 6 feet above the bow. Alright, so there's a ring 6 feet above. Alright, and we have that the rope is pulling it in, and so it's heading toward the dock. Okay, so we've got the boat is going closer to the dock. What should we expect this rate to be? Negative. What did I call this? I called this X. Alright, and it says the ring on the dock 6 feet above the bow. Or bow. I keep saying bow. Yikes. Okay, so our height here is 6 feet. Notice that that value doesn't change, right? That height stays the same. And it says the rope is being hauled in at 2 feet per second. You can call it Z, whatever you feel like. I'm going to call it, why not Z? We haven't used Z yet. And we have that that rate is 2 feet per second. Now, if my rope is being hauled in, is that going to be a positive 2 or a negative 2? A negative, because again, that length of the rope is shrinking. Alright, and they want to know how fast is the boat approaching when the amount of rope still out is 10 feet. Okay. So let's fill out all we know. What equation do you think we're going to use to relate all this information? Pythagorean theorem. Alright, so we know our equation is going to be x squared. Again, that 6 feet is a constant, so that's not going to change for us. And that length of rope is changing. We have that dz dt is negative 2 feet per second. Did I give us anything else? No. Alright, so what do we want? What are they asking? When the boat is going close to the dock. So what variable is I going to be working with? X. So we want dx dt. Specifically when the amount of rope is 10. So what variable is that going to be? Go when z equals 10. You know what? Go ahead and try that one. Finish that out. Don't ever be that person that rudely talks to the very nice people in the front office. Those ladies are so kind, you should never speak to them. Gee, I don't have X. I only have Z. How do I find X at this particular moment in time? Use that Pythagorean theorem to find your X value. Thank you. Alright, what do we get for our dx dt? What was it? And again, how fast is the boat approaching the dock? So we would say the boat is approaching the dock at 5/2 feet per second. So make sure you rewrite it to answer that question. Okay, now if you turn a couple pages within this, you'll eventually hit where it says related rates with trig. This is day 2. This is what we're going to be starting with next time. So if you really truly want to venture there, you may, but you're not required to. For your homework, I would like, for the SmartWorks work, I would like for you to do those 3 free response problems. Now again, the whole thing's not going to be related rates, but related rates will be within it. Hold your horses, wait. Okay, so I want you to definitely do free responses. That's supposed to be a star. Okay, and then you do what you need to extra to make sure you're successful. Okay, so I will be checking those 3 free responses, but do other problems that you need to make sure you fully understand the concept.
So all these 3 right now.
What do you say?
Yeah, 1, 2. Yeah, so these 3 right there. Yeah.
It's after example 13. So it says like 2011. So for sure do those 3 free responses and as needed. So do the free responses. So after example 13, you flip the page. See how it says like it's free responses? So there's those 3 pages there. Okay, so yep. So those 3 free responses are required 2011, 2008, and 2007. And then you do what you need to be successful. Does that sound fair?
Yeah.
Okay.